Okay, hello. These are the problems for chapter 10, which was stuff to do with restitution, basically a continuation of chapter 9. So we've got 1, 2, 3, 4, 5, 6 questions total here. And yeah, these are some pretty straightforward questions where it's basically just stuff from chapter 9, but now we're calculating the coefficient of restitution as well for all of the questions. So, we'll start with question 1. Two super soldiers throw shields at each other that collide. Right before impact, shield A of mass 4 kilograms has a velocity of 12 meters per second, and shield B, 6 kilograms, velocity of 15 meters per second. So, if shield A is 8 meters per second to the left, determine the final velocity of shield B. And, yeah, so let's begin. So for A, we have, of course, MA VA plus MB VB is equal to MA VA prime plus MB VB prime. So we have MA, we have VA, we have MB, we have VB, we have VA prime. We just need VB prime is what we're solving for. So, and I forgot to write this. Right, and 15 meters per second left. So the final velocity of A is to the left. So quickly, we're going to define our positive as to the right. I don't know why I included up. That doesn't matter. But the positive is to the right. So we rearrange for VB prime, which is really easy. It's just going to be MAVA plus MBVB minus MAVA prime all over MB, right? And then we just plug in our numbers. So VB prime is equal to, so we have MAVA, MBVB, so 4 times 12, so 48 minus 6 times 15, minus 6 times 15, minus MAVA prime, so MA is 4, VA prime is negative 8, so plus 4 times 8, which is, 4 times 8, 32, plus 32, and then divide all this by the mass of B, which is 6, we get a velocity of negative 1.67 meters per second, right? And that's how you solve for A. So if you wanted to make a diagram for this, you would have shields collide initially, and then afterwards they go like this. You have 12 and 15, and then you have 8 and 1.67, like so, right? Well, okay, it's going left as well, so let's just change this arrowhead. They both travel left, like that. There's your diagram if you want to draw it out. You could draw it more professionally, of course, but yeah. But this is just me demonstrating here that you don't actually need a diagram for every single question, because sometimes it just wastes time. Anyways, B is asking us to calculate E, which we define as delta VF, or in this case it's V prime, so delta V prime over delta V, which is equal to, so VB prime minus VA prime, and let's put this in brackets, divided by, we have VA minus VB. And make sure you keep the order of these in mind here. This order does actually matter when doing calculations. So anyways, it's equal to negative 1.67 minus negative 8, so plus 8, divided by 12 minus negative 15. So put that into the calculator. We get 0.235 is our coefficient of restitution. And that's the entire question. So yeah, that is the entire question. Now, on to question 2. We have the diagram here alongside it, right? So Newton's cradle is a fun toy in, I'm sure you've probably seen this. I'm sure a physics professor of yours has had this on their desk before or something in high school. At least mine did. So you grab your first ball, and then you drag it a certain distance, you let it go, it hits this, and then the forces carry all the way here, the momentum velocity carries all the way to the nth ball, and then the nth ball goes up, and it'll be at the same angle, kind of. Obviously, there's some energy loss, like friction and stuff, and heat. So obviously, nothing is 100% efficient, but yeah, it's fine. So anyways, sphere 1 is released from the dashed position and strikes sphere 2 with a velocity v1. Write an expression for the velocity vn of the nth sphere immediately after being struck by the one before it. The coefficient of restitution for all the collisions is e. So we need to consider our scenario. We have m1, v1. So we have a v1 and we have a v1 prime. v2 is 0 initially, and v2 prime is something. So we can write that out as m1 v1 is equal to m1 v1 prime. I forgot the subscript thing here, plus m2 v2 prime, right? Because we do not have a v2 originally, right? And quickly here, we have identical balls, meaning that all the masses are the same. So we can just change this to m like this, and that means all the masses cancel, like so. So we're left with the fact that v1 is equal to v1 prime plus v2 prime, and we're looking for v2 prime here because we want vn of the nth sphere. So we would rearrange this into v2 prime is equal to v1 minus v1 prime, like so. So we know that now we look at our coefficient of restitution equation, right? We have E is equal to, from above, we have a delta VF over delta V. So we have V2 prime minus V1 prime, right, over V1 minus V2 is just 0, so we ignore it. So it's over V1 like this, right? And if we rearrange this for, again, we rearrange it for V2 prime, we get that V2 prime is equal to, so it's E times V1 plus V1 prime, like so. Now, as you can see, we have two equations. So we just plug in, here, right? Which gives us that E V1 plus V1 prime is equal to V1 minus V1 prime, like so. And yeah, so this will become, and now we, what should we call it? We isolate for V1, so plus V1 prime, for V1 prime. So plus V1 prime here, minus E V1, right? So we're going to get 2 V1 prime is equal to 1 minus E V1, like so, right? And yeah. 1 minus, and this is a half, so we can just put a half out front here. Half 1 minus E V1. Right, so we have a expression for V1 prime, which we can then take into our equation up here, right? So taking this equation here, like this, and then minus this, right? Which we can then drag out a V1 from. So this becomes 1 minus this V1. And then we distribute out the half. So it's 1 minus a half plus a half E. So yeah. So 1 minus a half. So a half plus a half E. So we can drag out a half from this. So V2 prime is equal to a half 1 plus E V1. Like so, right? Now, there are a few ways to prove this for the nth v, right? We have this expression. Now, if we were to do this for the third velocity, so for the third ball, and then the fourth ball, the fifth ball, etc., right? We would find that we get Vn is equal to a half 1 plus e, and then this whole term here, like this, is to the power of n minus 1 v1. So these each get a v1 term into them, right? If we were to continuously solve. Now, there are a few ways to prove this. One way is from Calculus 1. What's it called? You can use... What is the method called again? It's that one proof by induction. Yeah, you can use induction to prove this. I remember my friend did in when he solved it in the seminar. You can also just like go get a v3, and then you'll see that you get... So here we have like vn, and this should be vn prime, but it doesn't really matter. Vn prime, right? So we get that Vn is equal to this term. And here you can see that n is equal to 2. So 2 minus 1 on this gives it to the power of 1. If you were to get V3, you'd get the same thing squared, right? Because if you kept building up the equations, you have, when you eventually get to like your V3 thing, you'd have a V2 prime here, right? And then you just substitute in this into V2 prime, right? Which gives you a half 1 plus e squared v1, right? And then the same thing for v to the 4. You'd have your v3 is equal to this thing squared v1. You'd plug that into your v4. This is really a yeah, this is a nice question, because, well, it was annoying to do, but you basically repeat this process again, and you keep solving for these e's with your new velocity. So here you'd have v2 as your v2 prime is your v1, and then you'd have v2 double prime plus v3 prime, or however you want to denote it, right? And then yeah, you'd do the same solving thing where you're, so in that case it would be v3 prime, and you solve for v double prime to plug into this equation, which you get through the coefficient of restitution equality. So equating this and this for v2 prime, and then you get v1 prime, and then you plug it into this, which gives you the thing. Yeah, this is the form you're going to get in the end. The actual, like I said, you can use induction to prove it. If you can recognize that this has to be to the n minus 1, right? Like this is 2 minus 1. If you wanted to really properly prove it, you'd do the v3, and then you'd see that the power increases by 1 around this first term. So then you'd be able to recognize that it's n minus 1, and then you could do your induction from there, or you could do your fourth case to prove the power increases by 1 each time, right? Nice and easy, just like that. So on to question 3 now. On to question 3. We have a BB ball is shot from a BB gun from point A with an initial velocity v prime at an unknown angle. Or sorry, this is not v prime. This is v naught at an unknown angle theta. The ball follows the initial path from A to B, horizontal range L1. It then strikes the ground at B, bouncing again to land at C at a range L2. The coefficient of restitution of the impact between the ball and the ground is E. Determine expression for the distance L2. So as you can see, these are really no number questions. Nice and theoretical, you know. So at A, we have a V naught, like so. It's launched from A, right? Yeah. So we have a V naught here, which means we have an angle theta here. And then it lands here like so. Right? So using kinematics here, in the y direction, so in y, at A, and this is at point A. So point A, in Y, we have gravity, right? We don't have time, but we can solve for time. We have V naught in Y, which is just V sine theta. And yeah, we can solve for V. So we have that. Also, keep in mind that how this works is that your Y velocity here will be equal to your Y velocity here. That's just some theory thing. So we get that V naught in Y is equal to, and this is negative V naught in Y. Negative V naught in Y is equal to V naught in Y minus GT, right? And we're solving for T here. So we get that T is equal to, so if we do this rearrangement, we go minus V naught Y on this side and then divide by negative G. We get 2 V naught Y over G, like so. That is our time, which we can then plug into our x direction here, where we have, using the distance equation, we have no acceleration in x, by the way. So we get v is equal to d over t. V is equal to d over t. We have t, we have d, we want v, right? So v is, or d is L1, and then divided by this, like so, right? And this is specifically v naught x, which is v cosine, right? So this is v naught cosine theta, and then v naught y, we can replace the y with sine theta, like so. This is a division, so the g is on top, or we're rearranging for L, sorry. So it's v is equal to d over t. So we would just multiply over by time. So this is 2 v naught. So it becomes, if we rearrange this, right, we get 2 v naught squared cosine theta sine theta. And also, if you see here 2 cos theta sine theta, we can simplify this into sine 2 theta. So I'm going to do that just for the sake of keeping things clean. Sine 2 theta over g is equal to L1, right? Now we have L1. So we get a collision here, which means there is restitution. But, yeah. So this has a change in Vy and not Vx, because the line of impact is, this is the line of impact, and it's y, right? This is just, this is the point of contact is in x, and that's from the theory video. So anyways, now we're at from B to C, right? We're going to have, again, using kinematics. So for point B, we have that V naught x is V naught cosine theta, and then V naught y is, we're going to actually have the coefficient of restitution times V naught sine theta for V naught y, because the coefficient of restitution is what changes the y velocity, right? So, and remember, we're solving for L2. So we'll start with the y direction. So we have that we actually get the same exact expression for time, again, which wouldn't you know it, right? And we can put in a sine theta here, right? Wouldn't you know it? It's the same exact expression. Okay, actually we're not going to put in a sine theta. We're going to keep it as y, because we have our new thing for y, or for v naught of y. V naught y is equal to e v naught sine theta, right? So yeah, we'll sub that in eventually. And now we go to the x direction. So we're solving for L2. So again, we're going to use v is equal to d over t, and I'm just going to do that instantly. So it's vt, right? And we have v naught x is equal to, so this is v naught cosine theta t. We know that this is t, so this is t, and we'll put an x, a star there. right? So this becomes V naught squared because we split this into V naught E sine theta, like so. So get this gone, all over G, by the way. And then again, we can make this into 2 sine 2 theta over G, right? And then, yeah, so this is equal to 2E, or this is equal to V naught squared sine 2 theta E over G. And then we know that L2 is equal to E L1, right? And the reason we know this is, if you think about it logically, if we bounce this much, right, and then the restitution occurs where the y velocity is lowered by a factor of e, right? Like it's multiplied by e, which makes it a less number, a smaller number. That means that the distance, horizontal distance, should be affected in the exact same way, right? So we know this, which means putting our two equations together, where we have L1, which is V naught squared sine 2 theta, right? And, or no, sorry, I don't know what I'm saying. V naught squared E sine 2 theta, without the E, is L1, right? I got ahead of myself. So if we rewrite this with the E out front, E V naught squared sine 2 theta over G. If we look at L1, we have V naught squared sine 2 theta over G. So this is just L1. So L2 is equal to E L1. And that is, for this scenario, an expression for L2, where L1 is equal to V naught squared sine 2 theta over G. And make sure when you're doing questions, look for like shortcuts like that in your simplifications, right? Because I could have left it at cosine 2 sine theta, cosine theta, but instead I simplified it to sine 2 theta because of trig identities that have been burned into my mind because of calculus. But it's okay because calculus is great. Anyways, on to the next question. On to the next question. This one is, so car B is Car B weighs 3,200 pounds and travels west at 30 miles an hour and collides with car A, 3,400 pounds, traveling north 20 miles an hour as shown. Two cars become entangled and move together as a unit after the crash. Compute V of their common velocity immediately after impact and the angle made by the velocity vector with the north direction. So what's the angle with respect to north, right? So it wants this angle, like so, theta. Now what you could do, if you wanted to, is draw out a diagram for this question. I drew diagrams for the questions in the chapter 9 problems. So I'm not going to do it in chapter 10 because I just want to showcase that you can actually solve these questions without a diagram. And I think that drawing a diagram, unless explicitly asked for sometimes, is a waste of time. So we have MA, VA, right? We have our X and Y direction. So X and Y. And I'm going to take this way to be my positive, right? If you're not going to draw a diagram, I would at least take the positive, like specify your positive direction, just because it helps you remember things and it also helps your graders. Yeah, it helps your graders keep that stuff in mind. So we know that momentum is in components, right? Which means we're going to have to do it in the X and the Y directions. So very, very, very easy. So in the X direction, we have nothing from A, actually, right? We just have that MB VB is equal to MAB VAB, right? So, and these are all weights, not, these are weights, not masses. So we need to compute those. So MB is equal to 3,200 over 32.2, which is equal to, let's see, 3,200 over 32.2 is equal to 99.4 slug. 99.4 slug. We have that MA is equal to, so 3400 over 32.2, which is 106 slug. And then we have MAB is equal to, so 3200 plus 3400 is 6600 over 32.2, which is 205 slug. 205 slug, like so. You could have also gotten it by adding these masses together. Whatever works for you, right? I forgot to write the 3400 over 32.2 equal to this, and then this is 6600 over 32.2 is equal to this. So we have our masses, we have VB, we want VAB. So all we do is divide out by, so we would divide 99.4 times, what is it, 30, negative 30, because it's going away from a positive, and then divide by the mass AB, so divide by the 205, which gives us a, in the x direction, a VAB is equal to negative 14.5 meters per second, or miles per hour. And then in the y direction, we're going to get the same thing. We're going to consider, so we have MAVA is equal to MABVAB, right? So divide by MAB on both sides. We're going to get that VAB is equal to, so we have 3400 times 20 divided, or not 3400, sorry. It's supposed to be 106 times 20 divided by 205, which gives us 10.3 miles per hour. So adding these together, we have VAB is equal to negative 14.5, and we can introduce I and j coordinates here because we know it's a vector. So negative 14.5 I plus 10.3 j. And it's also asking for the angle, so we can just use tangent theta is equal to, so we go like this in the I and like this in the j. So we have this angle. The I is the, yeah. So our vector would be like this, right? So the angle it makes would be from here to here, meaning that the opposite is the I and the adjacent is the j. So tan theta is opposite over adjacent, so negative 14.5, oops, I'm on the negative 14.5 over 10.3, which is opposite over adjacent, right? Which gives us a theta, which is equal to, so let me see here, tan inverse of this over this gives us a theta of negative 54.7, right? Which is, if we consider it, because the way it's calculated is in quadrant 4. So we have our angle like here. So we're just going to take it to here, which we do by, we can just add 90 to it, or not add 90 to it. Yeah, we will just flip the sign on it, basically. So it's 54.6 degrees. We have our angle here. We want to take it to here with respect to this y, right? So you would just add yeah, you would just flip the sign, because what you're doing basically is adding 90 degrees to it, which gives you like the full angle from here to here, and then you're subtracting this 90, or you're taking I'm a little mixed up. You get an angle. Let me just clean up this diagram here quickly. So we have like this, our vector. The angle we got was down here, Adding 90 to it brings it into quadrant 1. And then if we want to bring it over here, right, we just do 90 minus this angle, which gives us our angle with respect to this axis. Because by taking it, subtracting that angle from 90, you're basically taking this area as your new axes, right? You're flipping the whole thing by 90 degrees. So that gives you your new angle here with respect to this line instead of respect to this line, right? I hope that made sense. Anyways, that's how you solve that. So on to the next question, Q5. Goodbye. We have, no, not this one. This one here. So, oops. Determine the final velocities v1 prime and v2 prime after the collision of the two cylinders if v2 is equal to 2.4 feet per second, coefficient of restitution is 0.5, shaft is smooth, so no friction. Also determine the percent n of the original energy lost during the impact. As you can see, we have x is this way to the right, so v2 is negative, and v1 is 0.8, and the weights are here, 1.5 pounds and 2 pounds. So this is a central impact, and coefficient of restitution is 0.5. So keep that in mind. So there are two cases that could technically occur here. And one case is that one case is that they both go to the right after the collision, and the second case is they both go to the left after the collision. You want to assume the positive case. So you assume they both go right after the collision, right? And then the signs will work out. Like if you assumed V2 was positive and you got negative, I mean, if you assumed V2 goes to the right and you got negative, that means your assumption was wrong. V2 goes left, right? That's just how directions work in physics. So we have M1, and again, we're going to have to calculate this. So M1 V1 plus M2 V2 is equal to M1 V1 prime plus M2 V2 prime, right? And then quickly here, we can get that M1 is equal to, so 1.5 over 32.2, which gives us a mass of, so 1.5 over 32.2. 32.2 is 0.0466, 0.0466 slug, and then M2 is equal to 2 over 32.2, which is 1 over 16.1. I mean, that doesn't really matter. It's not like I could. So that's equal to 0.0621 slugs. So there we have our masses now, right? We want V1 prime and V2 prime. So we're assuming that these two velocities are positive. We know this one's negative and we know this one's positive. So we take our E, which is just V2 prime minus V1 prime, bracket like this, over V1 minus V2, right? And we know that this is equal to 0.5. So we have 0.5. Yeah, we can get what the difference of VA2 minus V, or we can get like the difference in VA prime and VB prime, right? So we get, if we, so V1 minus V2 is 0.8 minus 2 point, or minus negative 2.4. So that is 3.6, right? Yeah, that is 3.6. So 0.5 times 3.6 gives us 1.6 is equal to V2 prime minus V1 prime. And then now we just we solve for V2 prime. So V2 prime is equal to 1.6 plus, or we can solve for V1 prime. V1 prime is equal to V2 prime minus 1.6, right? Just like that. And then we can substitute v1 prime, which is equal to v2 prime minus 1.6, into this equation, giving us one unknown as v2 prime. And then using algebra, we rearrange for v2 prime. So we have two v2 prime terms here. So then we just factor out v2 prime and then divide by the term here, which gives us that v2 prime is equal to, so if you were to do the whole algebra, you would get, so let's see, what's the weight here is, okay, so you get that v2 prime is equal to negative 0.34, right? And then you would just use this equation here, v2 prime minus 1.6, to get v1 prime, which is just equal to, and as you can see, they're both negative. It's negative 1.94. And these are both feet per second. So the algebra for v2 prime is like kind of ugly, so I didn't want to type that out. That's basically it. And now for the percent energy loss. Oops, that's supposed to be here. Because we want the percent n, energy loss. What that equation is, so percent is equal to, so T1 minus T2. And that's all over T1, where T is kinetic energy, of course. So T1 is half mv squared. And of course, there's a VA and a VB. So it's half MAVA squared plus half MBVB squared. And then T2 is half MAVA2 VA prime squared, or not VA, I don't, half M1 V1 squared plus half M2 V2 squared, and that's for T1. And then T2 is half M1 V1 prime squared plus half M2 V2 prime squared, right? And then you would subtract the 2 and divide by your T1. So if I were to quickly calculate that here using my masses, so what were the masses? 0.0621 and this. So half, so 0.5 times M1, which is 0.046, times V1, which was 0.8 squared, plus a half times M2 squared times V2, which was 2.4 squared. It's negative, but the square cancels negative, so it's whatever. So we get a T1 is equal to 0.19. And then T2 is, so it's 0.5. I'll just put this on the outside. M1, which is this, times, so V1 is 1.94, V1 prime is 1.94 squared, plus our second mass times 0.34 squared, which gives us 0.09. So we get 0.19 minus 0.09 divided by 0.19, which gives us a percent of 52.9. So percent is equal to 52.9, right? That's the percent we lose, and it's in percent. Where T1 was like the sum of, okay, I don't have the sum of half mv squared, and then T2 was equal to the sum of half m v prime squared, like that, right? And then this was equal to 0.19, and this was equal to 0.09. Yeah, and then you do the difference and divide by T1, you get a percent of 52.9. That is another question done. And finally, on to the last one. Okay, this one. So the ram of a pile driver has a mass of 800 kilograms and is released from rest from 2 meters above the top of the 2,400 kilogram pile. Ram rebounds to a height of 0.1 meters after impact. Calculate velocity, VP prime, of the pile immediately after impact, the coefficient of restitution, and the percentage loss of energy due to impact. So again, we're going to have to do the energy, we're going to have to do the coefficient of restitution, and the impact. So this question is actually going to be mixing chapter, was it chapter 7, work and energy? I don't remember. It's mixing conservation of energy and conservation of momentum. And you can get many questions that are like this in class, in exams. So this is a good example to teach that. So there are 3 phases, right? So from phase 1 to 2, the pile drops 2 meters and then it impacts, right? Or we call phase 2, so I'll type them out here. So we have phase 1 is the initial position. So this is 2 meters above, right? Phase 2 is before impact. Phase 3 is after impact. And phase 4 is final position, right? Those are the phases. So now in phase 1 to 2, and then we have 2 to 3, and we have 3 to 4, right? In each of these phases, we have 2 options, either conservation of energy or conservation of momentum. And that is true for each phase, like so. Now, which one are we going to be using for each phase is the real question, right? So phase 2 to 3, an impact occurs. And when an impact occurs, what do you think of? You think of conservation of momentum. So for phase 2 to 3, we're going to have conservation of momentum. Now, what about phase 1 to 2, right? Well, we have a change in position, no information on time, right? That makes you think of conservation of energy, which is forces over time, right? And what about 3 to 4? Again, we have a change in position, no impact or anything. So that means, well, it's conservation of energy. And that is how the question is laid out. And let me add that 0.1 meters above, right? So we have 3 parts to calculate basically. Phase 1 to 2, phase 3 to 4, and phase 2 to 3. And you can do these. You'll have to see what order these have to be done in to be able to get everything you need. So we have T1, and this is phase 1 to 2. So phase 1 to 2, that's 1 to 2, like so, right? So we have T1 plus V1. We're using conservation of energy here. We have no external forces, so there's no work, right? Is equal to T2 plus V2. Well, T1 is 0, right? Because it's from rest. T2 is half mv2 squared. And V2 is, oh yeah, we're also going to be taking our, we need to establish a datum to be able to do like our our energy stuff, right? So let's think about it. We could take our datum to be 2 meters below, right? That would give it an initial potential energy and no final potential energy. Do we want that? I don't know. What we could do to make it easier is if we put our datum up here, we get that there's no initial energy at all, actually, right? Because there's no kinetic and there's no potential because it's right on the datum. And that would make our V2 negative. Well, okay, actually it doesn't matter because here V2 would be positive and then you would subtract it anyways from like, you know, the, so it doesn't actually matter, but this datum will make the later parts easier on us anyways. I believe so because, yeah. So we can substitute now in our equation. So we have half mv squared plus mgh. And then we know that the, also these are, yeah. So we have the masses of these things. So m here is 800. So this would become 400 v squared plus m and h. So h is -2 down here. We're here. for phase 2. So negative 2 meters down. And m is 800. So this is minus 1600 g. So to solve for v squared, we would just go square root of 400 g, right? That's how we would solve it, is equal to v. So this is equal to, so let's see, square root of 400 times 9.81 gives us a velocity here, or not 400, because 1600 over 400 is not, yeah, it's not 400. 1600 over 400. It's 4g, square root of 4g. 4 times 9.81, we get a velocity of 6.26 meters per second, right? And considering our datum, this velocity is going to be going downwards. So this is negative 6.26 meters per second. Now we look at our conservation of momentum, right? Where we have m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime, right? Where v2 and m2 are related to the pile, and m1 v1 are related to the ram. So the ram, I mean the pile is initially at rest. We don't know the final velocity of the ram, because this is the velocity of the ram directly before impact, right? So we don't actually know what the final velocity, the velocity of the ram after impact is. So to do that, we have to use our 3 to 4 calculations, which is again more conservation of energy, right? I know there's a lot of work here that I just kind of like slowly erased over time. I won't do that this time so that you can follow things more easily. So we have T3 plus V3 is equal to T4 plus V4. Again, there are no external forces, so that's all fine and dandy. We know that V3 is 0 because right before impact it is, or T3, position 3 is down here. We can take a new datum of reference for this part. So this is our second datum for 3 to 4, right? So its potential energy is 0 initially. Its kinetic energy is half mv3 squared, right? And then let's think about afterwards. It rebounds to a height of 0.1 meters after the impact, and we're considering that to be our maximum. So that means that we have no T4 and we have no V3. So this is just half mv squared is equal to mgh. As you can see, masses cancel. It's going to be 2 square root of 2gh is equal to v. And okay, well, I said I wasn't going to do that again, but I still did. So oops. And remember, 0.1 is positive above the datum. So yeah. So square root of 2 times 9.81 times 0.1 times 0.1. This gives us a velocity 3 of 1.40 meters per second. So now finally we can do phase 2 to 3, which is our conservation of momentum, and actually allows us to solve for the velocity of the pile, the coefficient of restitution, and the energy thing we can do after we do our coefficient of restitution thing. So yeah. So this will be MR, right? MR, but we're going to call it M2V2. M2V2 plus M3V3 is equal to M2V2 prime plus M3V3 prime, where 3 is the pile and 2 is the ram. So this is initially at rest. We have V2 prime, which is this here. So let me label these. This is V2 prime. This is just V2. We're solving for V3 prime, right? So we would just go M2 V2 minus M2 V2 prime divided by M3. And the pile is 2,400 kilograms. So plugging that into our calculator, and keep the signs the same as what you've gotten, right? We get that V3 prime is equal to, so we have 800 times this thing here, negative 800, or 800 times negative 6.2, minus 800 times 1.40, and then divide by 2,400. We get that is equal to negative 2.56, negative 2.56 meters per second, right? So that is the first part. So that's A. Let me label this here A. And now for B, let me just put this question up a lot. Okay, there. Now for B, we need the coefficient of restitution. That's just E is equal to, so it's, remember, this is only to do with the impact. So you can ignore a V1, you could ignore anything else, the energy stuff. So we have V3 prime minus V2 prime. And then this is in brackets, as we will be doing a fraction, divided by V2, right? Because V3 prime is just 0. I mean, V3 is just 0. It would have been V2 minus V3, but V3 0. So then we get this is equal to, so I forgot to write the negative. So we have negative 2.56 minus 1.40 divided by, and then initially it was negative 6.26, right? And then this is equal to, so we just do this minus this divided by negative 6.26. Gives us a coefficient of restitution of 0.631. And for part C, we want the percent energy loss, right? So of the impact. So again, we're going to be looking at, so percent is equal to T2 minus T3 over T2. So we have T2 is equal to half mv2 squared, right? Because initially, or not T3, these are like the energy. Okay, the labels are getting a little confusing now, because here I had 3 as the pile, 2, but this is not energy of the pile. Energy of phase 2 minus energy of phase 3 over energy of phase 2. Yeah, whoever's watching this is smart, so I'm sure you've kept track. So the kinetic energy at first is just half mv ram squared, because the pile had no energy in phase 2, and then in phase 3 we have half mv squared, and this is a sum of half mv squared, right? So if you if you do the calculation, so half mass of the ram was 800, velocity 2 of the ram, so was the 6.26 number, squared, so we get 15,696, right? And then this is equal to, so 0.5 mass of the ram times the velocity of ram. The second time was the 1.40 plus mass of the pile, which was 2,400, times its second velocity, which was the 2.56 squared. So 2.56 squared, like so, gives us 8394. And we just go 8394, or we go 1596 minus 8394 divided by 15,696 gives us a percentage of 45. So the percent here, which we can go back up here, is equal to 45.1%. And if you're like calculating things alongside and you're off by like a percent error, I like to say if you're off by 5% from the answer that is given, you got the question right. Because not everyone carries things in their calculators the same. Not everyone's calculators actually calculate the same numbers because of like rounding error stuff. Okay, well, I don't know how true that is. But whatever, that doesn't actually matter. Basically, if you're within 5% error, so if you got like 44%, 46%, right? If you're within percent error, you're fine. You got the question right. So anyways, those are all the questions for chapter 10. I hope you learned something. Thank you for watching, and bye.